If somebody asks you on the street to name any physicist you know, I could imagine many of you would table names like Albert Einstein, Isaac Newton, Galileo Galilei, or Stephen Hawking. Well, no doubt they are famous. More than just well-established physicists, these men had made major contributions to the society as well. Einstein, for instance, was deeply involved in campaigning for the civil rights of African Americans. Galileo, famous for his scientific achievement such as the demonstration that all objects fall with the same acceleration by dropping two balls of different masses from the top of Leaning Tower of Pisa, the very same scientific achievement caused his controversy with the church, was in fact a devout Christian who saw not a divorce of religion and science, but only a healthy marriage. In 1642, the same year when Galileo passed away, Isaac Newton was born. The world is never short of geniuses. Isaac Newton, the hero of today's lecture, was also a staunch Christian who thought of God as masterful creator. Newton's most famous publication is arguably the Principia, where he outlined the laws of motions we are going to learn in this session. Lesser known, Newton also published a number of books with regard to literal interpretation of the Bible, but that's out of point for now, so let us get back to Newton's law of motion. In Lecture 4 series, we learn how objects move, whether the motion is uniform or accelerated, whether it is linear or circular, etc. But we never concern ourselves with what causes the object to move in the first place. Now imagine this box. It lays motionless, stable, untouched on the floor, with no external influence whatsoever. Guess where you'll find the box an hour later? Well, provided nothing happens to it, nobody touches it, of course you will find the box on the exact same spot an hour later. How about tomorrow? Where will you find the box tomorrow? Again, provided nothing happens to it, nobody touches it, of course you will find the box still on the exact same spot tomorrow. Okay, this doesn't sound like a smart physics discussion, does it? But that's exactly what I would like to illustrate here. Taken from the mouth of Newton himself, everybody continues in states of rest or of uniform motion in a right line, unless it is compelled to change that state by forces impressed upon it. Unless a force or forces are exerted on the box, we should expect the box to remain motionless on the very same spot, guaranteed. Or as Newton pointed out, if the box has somehow been moving at constant velocity, it will continue to move at that constant velocity. There are cases where forces are exerted on the box, such as these two men pushing the box with equal strength but in opposite direction. Will the box change its state, that is its position and its velocity at later time? Obviously, it is not going to be the case. The forces cancel each other, that in effect, the box experiences zero net force. So in plain English, if the total force acting on the object is zero, the object will stay still if it is motionless to start with, or continue to move at constant velocity if it is already moving to start with. This weird-looking notation is a capital Greek letter called sigma, which is used to denote the sum or total of something. So sigma F means the total force. F stands for force. When the total force acting on an object is zero, that is sigma F is equal to zero, the object will stay still or continue to move at constant velocity. There is a technical jargon to describe the situation when sigma F is zero, or when the forces acting on the object cancel each other. It is called equilibrium. So please remember this: when an object is in equilibrium, the object will stay still or continue to move at constant velocity. If you pay attention, this is the fourth time I repeated Newton's first law, albeit in a slightly different phrase every time. Very important indeed. What happens if the net force acting on the object is not zero? Newton then said, the alternation of motion is ever proportional to the motive force impressed and is made in the direction of the line in which the force is impressed. Now allow me to put into illustration what Newton's meant. Look at the image. Now there's only one man pushing the box, and hence, the box experiences a net force to the right. It shouldn't take much mental capacity to imagine that if the box is initially standing still, the force will push the box to the right, gaining speed along the way. If the box is already moving to the right when the force is applied, the force will cause the object to move to the right with even higher speed. Or, if the box is already moving to the left to begin with, the exertion of the force to the right will cause the object to decelerate and stop. If this force is constantly being applied to the right, the box will then start moving to the right and gaining speed. Thus, in effect, the force has caused the object to reverse its motion. So V0, which is the initial speed of the box, could be 0, that is to say the box is not moving initially, or non-zero, that is to say the box is already moving. The box could be moving along or against the force. In any case, the force has caused the box to either speed up, slow down, or change its direction of the motion. That is what Newton's meant by alternation of motion. For an object to alter its motion, force must be impressed or applied on the box. If you recall from Lecture 4 series, isn't speeding up, slowing down, or changing of one's direction over time what we call acceleration? So although Newton didn't use the term acceleration in his original writing, it is kind of implied that net force causes the object to accelerate or decelerate depending on the relative direction of the applied force to the initial motion of the box. Or put it the other way around, for acceleration or deceleration to occur, there must be net force exerted on the object. The proportionality factor between the net force and the acceleration is mass, denoted by m here. It is a scalar quantity. It is one of the base quantities. It has SI unit kilogram, remember? Hence, we have the famous F equal to ma equation. Acceleration is a vector quantity. Mass is a scalar quantity. Hence, by construction, force will have to be a vector quantity whose direction is the same as the direction of the acceleration. Indeed, as we illustrated just now, the exertion of force to the right causes the object to accelerate to the right. Now keep this in mind. Newton's second law relates dynamics, which is signified by force, to kinematics, which is signified by acceleration. So the left-hand side and the right-hand side are mathematically equal, but physically are not the same. No, you didn't hear me wrongly. I repeat, the left-hand side and the right-hand side are mathematically equal, but physically are not the same. Let that sink in for a moment, cause this is an important concept. If somebody asks you, is the force equal to m times a? The answer is yes. Force is related to acceleration through the proportionality constant known as mass. But if somebody asks you, is force m times a? No, because one is a dynamical quantity by nature, while the other is a kinematical quantity. They are related, but they are not the same. Just because two things are related, it doesn't mean they have to be the same, do they? In kinematics, we learn position. The change in position over time gives rise to the notion of velocity, and the change of velocity over time gives rise to the notion of acceleration. Why didn't we go further to discuss the change of acceleration over time to come out with another notion? Well, because we do not need to. Force is proportional to acceleration, and as I mentioned earlier, force is as physical as you can get. All the physical interaction that is happening around you are forces interaction. You are grounded and not floating around because of gravitational force. You are able to sit down comfortably on the chair without falling through it because of the normal force that the chair applies on you. You are able to walk normally along Orchard Road because of friction force between the pavement and your sole. When you weigh yourself on the scale, you are reading the normal force between you and the scale. Your compass tells you the north and south direction correctly, and hence you are able to navigate yourself out of the jungle during BMT because electromagnetic force interaction between the compass and the Earth's magnetic field, and the example goes on and on. These are all forces in action, and these forces are proportional to the acceleration. Gravitational force is proportional to gravitational acceleration, for instance. The next thing we would like to discuss is mass. It needs force to accelerate an object, that's pretty clear. But given the same amount of force applied, you will imagine that different objects would accelerate differently. Pushing a wooden crate of this size is probably not much of an issue. It is not so anymore if the crate goes 10 times bigger. And it is a different ballgame altogether if you are pushing a marble stones instead of a wooden crate. The amount of force exerted is the same. What distinguishes one case from another is the mass of the object that the force is acted on. In that sense, the mass of an object is a measure of how easy or how difficult for that object to move. The technical term used to describe how easy or how difficult it is for an object to alter its motion goes by the name inertia. An object with large mass has higher inertia, and hence, it is more difficult to alter its state of motion as compared to another object having lesser mass or lesser inertia. In other words, you need more force to alter a motion of a more massive object to achieve the same effect as a lesser force would on less massive object. Literature refers to this physical understanding of mass as inertial mass. This is to be contrasted with another way to understand mass by way of gravity, which is called gravitational mass. We will talk about gravitational mass in future lecture. Another thing worth noting from this illustration is that mass is a quantity that not only it depends on the size of the object, small crate versus big crate, but also on the density of the object, wood versus marble stone. The size of the object, big or small, is described by the volume of the object. The density of the object, obviously marble is more dense than wood in this case, is denoted by another Greek letter called rho. In short, mass is equal to density times volume. I will let you work out the SI unit of density using dimensional analysis that we learned in lecture 2. The first two Newton laws deal with situations involving forces exerted on an object. An object experiences a force because it is interacting with another object. You will not expect a wooden crate to move by itself unless somebody is pushing it, will you? Of course, the nature of this interaction can be in contact, such as a man pushing a crate. The man's hands are thus in contact with the crate, or non-contact, such as interaction between two magnet bars or two electric charges. The former is what we are mostly dealing with in this course. The latter is a subject of study in Fundamental Physics 2 course. How did Newton account for this interaction? He did so in his third law, which said, to every action there is always opposed an equal reaction, or the mutual action of two bodies upon each other are always equal and directed to contrary parts. The man is applying a force, and this force is drawn on the crate's free body diagram as such. In reaction, the crate is exerting a force on the man of equal magnitude and opposite direction. This reaction force is drawn on the man's free body diagram as such. From my experience and encounter with students' difficulty, it seems that Newton's third law is arguably misunderstood most often. I will highlight some of most common misunderstanding with regards to Newton's third law. First, you may ask, which one is action force? Which one is the reaction force? Is the force that the man applies on crate that is the blue force so-called the action or reaction force? In this example, I mentioned just now that the red force, which is the force that the crate applies on the man, is the reaction force. Does that mean the blue force is the action force? The point is, action-reaction is just a nomenclature. They are not cause and effect phenomena. It does not mean that the man has to apply the blue force on the crate first and a split second later the crate would respond back with the reaction force. For all that matters, in reference to this diagram, the red arrow could be the action and the blue arrow the reaction force. In practice, both forces occur instantaneously the moment the man's hand pushes the crate. In short, do not concern yourself too much on which force is which. Second, some students tend to confuse Newton's third law with Newton's first law. As illustrated in the second slide, if two forces of equal magnitude act on an object, the net force will be zero and the object will maintain its current state. Now in this illustration, there are indeed two forces of equal magnitude opposing each other. How could the crate move? Shouldn't the crate stay motionless in accordance to Newton's first law? While both laws are correct, the crate will not move if the two forces of equal magnitude but opposing direction act on the same crate. That is, they act on a single same object. Action-reaction forces, though they are of equal magnitude and opposing direction, act on different objects. The man applies the blue force on the crate, hence the blue force acts on the crate. The crate applies the red force on the man, hence the red force acts on the man. As far as the crate itself is concerned, there is only one force acting on it, the blue force, which goes unopposed. That's why the crate is still able to move. In conclusion, action-reaction forces are always equal in magnitude but opposite in direction, and they have to act on different objects. Is so far alright? I brought up the term free body diagram. What is free body diagram? The idea is straightforward. Let's come back to our crate example. We remove the man pushing the crate from the picture so as not to confuse ourselves since we are only concentrating on the crate free body diagram. In a typical situation of a man pushing a crate, a number of forces can easily be identified. We will examine these forces in details in the next lecture. But for now, let's briefly go through them one by one. First, we have the pushing force applied by the man. Second, the crate will definitely experience a gravitational attraction from the earth. This gravitational attraction comes in the form of weight. Third, because the crate is in contact with the ground, it will drag across the ground as it is being pushed. there's a friction between the crate and the ground. Lastly, because the crate weighs on a hard ground, the ground also provides a supporting force, which is called normal force, to keep the crate from sinking in. Free body diagram then provides a convenient way to draw these forces on a single point representing the crate. In doing so, these forces are now aligned to a Cartesian coordinate-like axis, and we can easily write down the net force along the horizontal or x-axis and the net force along the vertical or y-axis. As we have learned earlier in our encounter with other vector quantities such as velocity or acceleration, when you are doing mathematical operation onto vectors such as adding or subtracting vectors, you can only do so when they are aligned. We can subtract friction force from applied force to give us the net force along the horizontal. Notice how these forces are in opposite direction, hence they have to subtract each other. Similarly, we can subtract weight from normal force to give us the net force along the vertical. If we know the component of net force along the horizontal and vertical, we can compute as well the component of the crate's acceleration along the horizontal and vertical by way of Newton's second law. Finally, before we close this lecture, I would like to point this important thing out to you. If you think about it, what is the physical justification for all the forces to act on the same point in the free body diagram? Shouldn't the forces act on different points on the crate? Friction and normal force should act on the bottom surface. Gravity acts on the center of mass or center of gravity of the crate, and the pushing force slightly above the CG of the crate. Well, if you are thinking along that line, you are absolutely right. As a matter of fact, if you are to consider the crate as it is in reality, this will add complexity to the whole problem. For instance, the crate may still move, or topple to be more exact, even though the net force acting on the crate is zero, which seems like against Newton's first law. We will discuss this further when we touch on the rotational dynamics chapter in near future. But for now, as far as this lecture and the few subsequent lectures are concerned, we shall assume our object at hand as a point particle so-called. That is to say, we shall not concern ourselves with the size and shape of the object. It is to be treated as a point particle in which all the forces act on.